Hello students, welcome back. We're going to continue today, bless you, with Carbohydrates Part 5. Carbohydrates Part 5. Just a little review, just to get ourselves oriented. On last time, we talked about the different isomers. We have structural isomers like D-glucose and D-fructose are structural isomers. And then we talked about stereoisomers like D-glucose and everything else is a stereoisomer, but D-fructose is not a stereoisomer. Then we talked about enantiomers or perfect mirror images, D-glucose and L-glucose. And then we talked about isomers, stereoisomers that are not mirror images. They're called diastereomers. And then we talked about stereoisomers that only differ in one chiral center. Those are called epimers. For example, D-galactose is a 4-epimer of D-glucose. So we did this last time, and we also on last time we closed the ring of fructose. We took the 5-carbon and we'll attack the carbonyl to make the ring structure of fructose, and we call that alpha D fructofuranose. And so we really want to cover, there are three very important or three famous carbohydrates that you need to know the purinose form or the furanose form of. There's one more we're going to cover, one more important carbohydrate, and that's going to be a carbohydrate that has 5 carbons. And this carbohydrate looks like this. I'll just draw it first. So is this carbohydrate, is this going to be an aldose or a ketose? It's going to be an aldose. 2, 3, 4, 5. Okay. And this carbohydrate, all of the carbons have the R configuration. All of the carbons have the R configuration. It's an aldose because it has an aldehyde functional group there. So it's an aldose. Yes, this is an aldose. Now, does anyone know the name of this famous carbohydrate? It's found in nucleic acids. This carbohydrate is found in nucleic acids. Ribose, very good, very good. This is ribose, D-ribose. D-ribose. Okay. And so this is D-ribose in the straight chain form. Okay. And now let's partially close the ring. So let's draw the straight chain. So is this a Haworth projection or a Fisher projection? This is a Fisher projection. So what we're going to do, we're going to draw the straight chain or the open chain. We're going to draw it in the Haworth projection. So it's going to be like right before it closes. So let's look at this first here. This is going to be the OH. With its electrons, this OH is going to come around and attack. Oops, nope, not there. This OH is going to, these electrons are going to come around and attack the carbonyl there. Okay? And so then we would have a 1, 2, 3, 4, 5, a 5-membered ring. And so I'm going to number these carbons 1, 2, 3, 4, 5. Okay, now I'm going to go and draw the Haworth projection right before it closes. Okay. So I'm going to put carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. And I'm going to put the OHs. This is an O. This is the alcohol. That's the one that's going to do the attacking. Okay. And our OHs. Okay. Now this is ribose, the straight chain ribose in the Haworth projection. So it's like you're looking at the ring, projecting, the bottom of the ring is projecting towards you. I'm going to go ahead and put the H's here. I'm going to make them gray because they don't really matter right now. I'm going to put the H's. So when you look at this structure, you'll know. Let's number these carbons so we can see if things look the same. I'm going to use green. 1, 2, 3, 4, 5. Question for you. Let's see if anybody can remember this. When we close this ring, are we going to form a hemiacetal or a hemiketal? A hemiacetal. Why? How do you know it's going to be a hemiacetal? Because there's no ketone. We're starting with an aldehyde. If we start with an aldehyde and we close the ring, we make a hemiacetal. Everyone okay with that? Now, let's close this ring. So I'm going to make this smaller here so I can have room. Okay, and this should be easy to see here. What's going to happen? These electrons are going to attack the carbonyl, and then we're going to create the bond, just like before. Nothing new. So now let's close the ring. I guess I don't have to draw it again, but I'm going to. Since you have to, I'm going to draw it again. This is carbon 5, CH2OH, 5, 4, 3, 2, and 1. I'm going to put my ring oxygen here. And the OHs on ribose, they go down. And everywhere else is just the hydrogen. Hydrogen here. Hydrogen here, hydrogen here. Now on carbon number 1, for ribose, does the OH go up or does it go down? Exactly, it depends on if it's alpha or beta. So which one do you want to make, alpha or beta? Anyone. Make a choice, beta. So beta, is it going to go up or down? Up. Which is greater, 1 or 2? 2 is greater. Which is greater, A or B? B is greater. Which is greater, alpha or beta? Beta. So beta has to go up. Beta is on top because it's greater. So here we're going to put OH is going to go up. And then down we're going to have our H. Okay, now, what is the straight chain name of this carbohydrate? Anyone? Okay, you went right to the end. Exactly. Say that again. That's the name of it, exactly. That's the name of the entire thing. Beta D ribofuranose. Wow, you all understand this. Exactly. So this is beta D ribofuranose. So, of course, it's a furan. Why is it a furan? What makes this a furan? It has 5 members in its ring. Exactly. You can only say furan or pyran when it's in the ring form. Bless you. Everyone okay with this? And so those are the only 3 I'm going to draw. Those are the only 3 that I'll draw for you or I'll have you know on a test. Right. Glucopurinose, fructofuranose, glucopyranose, fructofuranose, and ribofuranose. Those are the only 3 that I'll actually ask you to show me the mechanism of. Okay? Yes, on the anomeric carbon, if the OH goes up, it's beta. On the anomeric carbon, if the OH goes down, then it is alpha. So let me just put one more thing here. This carbon here, this carbon is called the anomeric carbon. The anomeric carbon. And so that could go up or down. Now, this anomeric carbon here, is this anomeric carbon chiral or achiral? It's achiral. There are only 3 things on it. So if you flip it over, it's the same thing. So this anomeric carbon here is achiral in the straight chain form. But here is this anomeric carbon, is it chiral or achiral? It's chiral here, so it becomes chiral. It becomes chiral. And that's why you have to designate either alpha or beta. Only on the anomeric carbon. Exactly. Only the anomeric carbon determines alpha or beta. If any of the other OHs change, you have a different molecule. It's no longer ribose. If any of the other chiral centers change, it's not ribose anymore. Everyone okay with that? Okay. Before we leave stereo structures, there's one more thing I want you to know. We've drawn glucose. We touched on this in the lab. We've drawn glucose as a Hayworth projection. Now what I want to do is I want to draw glucopyranose in a Fisher projection. How do you do that? So I'm going to draw glucose in the Fisher projection. 1, 2, 3, 4, 5, 6, CH2OH. And so glucose is what? Right, left, right, right. Okay. Now this is glucose in the straight chain form. But what we want to do, we want to actually, oh, hope nobody wrote it. Okay, we're going to actually make a bond here, so the bond is going to be here. So I'm going to go here. Carbon 1 is going to connect with carbon 5 here. 1 and 5 go together via that oxygen.
So when you build that real bond, it's usually the alcohol connects, no?
Exactly. So let me go. Let me put it in the. Let me see if I can find the pyranose form of glucose here on a previous slide. Okay, here it is. Now here is glucopyranose. This red oxygen here, that's the bond. That's the bond. That red oxygen is the intermediate between carbon 5. I'll make this red. Carbon 5 and carbon 1. So there's carbon 1, oxygen, carbon 5. So if we go back to, that's the Hayworth projection. Now if we go to the Fisher projection, here's carbon, this is carbon 1, carbon 5. So carbon 1, oxygen, carbon 5. Everybody with me so far? Also on carbon 1, there's an OH. And so I'm going to put the OH for carbon 1. I'm going to make it kind of big here. I'm going to put the OH for carbon 1 right here. OH for carbon 1. Now the question becomes, is this, so let me go ahead and put it here. So this is D-glucopyranose. That is D-glucopyranose. Now the question becomes, is this alpha D-glucopyranose or is this beta D-glucopyranose? Okay, and this is how you determine. Oh, that is right. This is alpha. And the way you determine it, when you do carbon 1, for carbon 1 here, if the bond for carbon 1 is on the same side as the bond for carbon 5, if the OH for carbon 1 is on the same side as the O for carbon 5, if they're on the same side, we call this alpha D-glucopyranose. If they're on the same side, it's alpha. Okay. Now you see, let's do it here. I'm going to circle it here. Now you see the OH here that's connected to carbon 1 here, that bond. C bond OH. If this OH on carbon 1 is on the same side as this here, it's alpha D-glucopyranose. That's one way to explain it, but the easiest way is to just draw the other structure. So what I'm going to do now, I'm going to draw beta D-glucopyranose. You all probably won't have to draw it because if this makes sense, well, I don't have to draw that, Dr. Merritt, I understand that. So what I'm going to do here, I'm just going to, since you all probably won't, I'm just going to copy this. I don't like the copy because it's not kind of like not fair for you all. Since your paper can't do this. Oops. Let's see here. Copy, paste. There we are. Okay. Okay, now what I'm going to do here, I'm going to get rid of all of this. And now I'm going to get rid of the OH here on this side, and I'm going to put the OH on this side, on carbon 1. And so now, this is no longer alpha D-glucopyranose because it's on the opposite side as the C-O bond. So what's the name of this molecule? Beta D. And so that's the only thing you need to know about Fischer projection in the ring form, is how to distinguish alpha and beta when you draw glucose or any carbohydrate in the Fischer projection. Most of the time, you will never see carbohydrates drawn in a Fischer, the ring form drawn in a Fischer projection. They're mostly always Haworth projections. The only reason you need to know this here is for that test question that you'll have. Like I'll show you two of these and I'll say which one is alpha, which is beta. Or I should draw alpha glucose. Fischer projection. And that's all you need to know. But in most textbooks, or like if you read a paper that has carbohydrates, it's always drawn, most of the time it's drawn in the Haworth projection. Okay. Everyone okay with this? Excellent, excellent. So now, let's move on to something, it's still going to be carbohydrates, but something else. Let's look at some derivatives now of these carbohydrates. Derivatives. Okay, Okay, what I'm going to do here I'm going to draw a carbohydrate, but I'm not going to draw the whole carbohydrate because it's going to take a lot. But let's see if this makes sense to you all. I'm going to draw an aldose. So I'm going to put here, this is an aldose. And I'm not going to draw all the carbons. I'm just going to put a wavy line to represent all the carbons. So this could be a triose or tetrose. And I'm just going to put the first carbon and the last carbon. And so this is an aldose. Any aldose. That could be glyceraldehyde, it could be erythrose, or it could be glucose. I just don't want to draw all of the carbons, the intervening carbons, because they don't matter for this. Is everyone okay with that? Now what we're going to do, if ever you have an aldose and you oxidize this aldehyde group, so when you oxidize something, you can speak of oxidations in two ways. You could either add an oxygen or take away an electron. Take away electrons. It's the same thing. But this one is going to be really easy to see because it's easy to see the addition of oxygen. So we're going to add an oxygen to this carbon, and now it's going to look like this because we've added an oxygen. And that's why oxidation is so named. So we've oxidized the aldose. So here we have an aldose, but when we oxidize it, we change it from an aldose to an aldonic acid. So we change ose to onic acid. So when you oxidize carbon 1, you change the aldose to an aldonic acid. So you change the name of the carbohydrate to something ose to something onic acid. Make sense?
So if we did this to the last thing we drew, the glucose carbonate, drew the glucose carbon onic acid.
Okay, what we're going to do, when you do this, you don't do it to the rings. Okay. Because in the rings, it's not an aldehyde anymore. It's an acetal. So you can only do it to the straight chain.
Okay.
So her question was, so if we did this to glucopyranose, does it become glucose pyranosonic acid? And my answer is no, because you don't oxidize the ring. You oxidize the straight chain. So let's do that here, just so you'll see. So this time I'm going to actually draw it. I'm going to actually draw like glucose. Okay, 2, 3, 4, 5, 6. Right, left, right, right. Do I need to put the hydrogens there, or would it be okay with you all if I left off the hydrogens? Okay, so this is glucose. Well, we can just put D-glucose. Gluc, and I'm going to put a dash and then put ose. I hate when this gives me issues like this, because now I don't know why this is happening. Let's see here. Okay. So this is D-glucose. So what we're going to do now is we're going to oxidize that very first carbon. So O, OH, 2, 3, 4, 5, 6, CH2OH. Right, left, right, right. Okay, and I'm going to put here D, gluc. Okay, I'm going to leave the rest off for now because I'm going to ask you all a question. So I'm going to give you all about 20 more seconds to write this down. So here, this is carbon 1. This is carbon 1. We've oxidized carbon 1. So there's an oxidation that takes place. And this oxidation is easy to see because we just added an oxygen. Everyone seems to have this. Now my question is, this is my question for one of you. Let's go back. When you have an aldose and you oxidize carbon 1, you change the aldose to an aldonic acid. So you change the ose in the word to onic acid. Now if we go here, we started out with glucose and we oxidized carbon 1. So what is the name of this structure here? Rivers. Exactly, D-gluconic acid. Exactly. Can it be simpler than this? Is there a way for this to be simpler? D-gluconic acid. What if the aldose, what if it were galactose and we oxidize galactose at carbon 1 Enriquez? What would be the name of the carbohydrate if the aldose was galactose and we oxidized carbon 1? What would be the name of the new carbohydrate? Oh, can you help him? Gonzalez. Okay. The carbohydrate is galactose. We oxidize carbon 1. What would be the name of the new carbohydrate? Taylor. Galactonic acid. Make sense? Can't be. I don't know how to make that any simpler. Very good. Okay, let's do another one. So here, what I'm going to do, I'm not going to draw the whole carbohydrate. I'm just going to put here. This is our aldose and the terminal carbon. This time, we're not going to oxidize the first carbon. We're going to oxidize the last one. So the first carbon is still going to have an aldehyde up here, but that last carbon is going to have a carboxylic acid. Okay. Oh, I'm sorry. Well, I can just put an O there. It's going to have a carboxylic acid. And so here we would have the aldose. This would be the aldose. But when we oxidize the terminal carbon, when we oxidize that last carbon, then you're going to change the aldose into an uronic. Not just onic this time, but a uronic acid. So you convert it from an aldose to an uronic acid. So question goes to Sewell. So if our carbohydrate, Sewell, is galactose and we oxidize carbon 6, the very last carbon, well, if the carbohydrate is glucose and we oxidize carbon 6 to a carboxylic acid, what would be the name of the new, or the oxidized carbohydrate? What would be the name of the new molecule? Chapman, you oxidize carbon 6 on glucose. What's the name of the new molecule? Shaw? Say it again. Right, but you just don't need the O. It would just be glucuronic acid. Glucuronic acid. Make sense, everybody? So let's do one. Let's not do glucose since we just said that one. Let's do galactose. So I'm going to draw galactose. 2, 3, 4, 5, 6 CH2OH. And so galactose It's not right, left, right, 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 left, right, right. It's right, left, left, right, because it is a 4 epimer of glucose. So you just have to change 4. And so what we're going to do here to galactose, and so this is galactose, but is it D-galactose or L-galactose? D. How do you know it's D? Which OH? The 5th one, exactly. And so now what we're going to do, we're going to still have our aldehyde. 2, 3, 4, 5. And now we're going to oxidize, completely oxidize that terminal carbon. Right, left, left, right. And so this is D-galactose. Okay. Okay, here. Winters. We started out with D-galactose. We've completely oxidized carbon 6. Completely oxidized carbon 6. What is the name of the new molecule? Say that again. So you have her? Galacturonic acid, exactly. Galacturonic acid. And then uronic acid. Make sense? There is one more oxidation I'll need to show you. Okay, and on this one, we start out with an aldose. So we have here an aldose. And this time, we're going to oxidize carbon 1. And we're going to oxidize carbon, the terminal carbon. Wow. We're really oxidizing this thing. So we oxidize carbon 1 from the aldehyde to the carboxylic acid, and then we doubly oxidize the terminal carbon from the alcohol to the carboxylic acid. And so on the right, we have the aldose, and on the left we have the aldose, and on the right we have the alderic acid. We have the alderic acid. Everyone okay with that? Now this time I'm not going to draw the structure. I'm just going to draw the name. Okay? We have glucose. And then we're going to oxidize carbon 1 and carbon 6. Frith. We oxidize carbon 1 and carbon 6 on glucose. What's the name of the new molecule? Why inic?
Oh, sorry.
Glucaric acid. It's glucaric acid. Everybody okay with that? I'm not going to draw this because I think you understand what it looks like. Campbell. Let's say we start out with galactose. and we oxidize it at carbon 1 and carbon 6. What's going to be the name of the new molecule? Galacteric acid. Galacteric acid. Okay. Everyone okay with that? Excellent, excellent. Put your notes away. What is the general name of stereoisomers that are not enantiomers of one another? What's the name of stereoisomers that are not mirror images? Diastereomers. Very good, very good. Let's see here. The anomeric carbon of the straight chain of glucose. Is it chiral or achiral?
Achiral.
Achiral. Very good, very good. The anomeric carbon of the closed ring of glucose. Is it chiral or achiral? It's chiral. Is it alpha or beta? It depends. It depends. Which configuration is up? Beta. Very good. Very good. What's the name of the 5-carbon carbohydrate that's found in nucleic acids? Ribose. Very good. Very good. If you were to draw a carbohydrate, the ring structure of a carbohydrate in the Fisher projection, how do you determine if it's alpha or beta? Decide the OH is on. Which OH? Which OHs have to be? The first and the fifth. If the first and the fifth are on different sides, what is the configuration? Beta. Very good, very good. You all seem to understand this. Let's say you have an aldose and you oxidize carbon 1 and carbon 5. The aldose is converted into what? Alderic acid. What if you just oxidize carbon, the terminal carbon of the aldose? An alduronic acid. And what if you oxidize carbon 1 of the aldose? Aldonic acid. Make sense? Very good. Have a great day, you all. You all seem to have learned.